Hello everyone, welcome back to Nated Engineering. We are still doing Heat Engineering Science N3, and today we will be looking at steam generation. So before we start looking at how steam is generated, I want us to first look at boiling point. We know that the boiling point of water is the temperature at which water will start to boil, and it is 100 degrees Celsius. Most of us, if not all, knows about this. What I think most of us are not aware of is that there is a condition that must be met for this to be true, and that is pressure. The boiling point of water or any liquid depends on the pressure which that water is subjected to. Water boils at 100 degrees Celsius only when the pressure that it is subjected to it is atmospheric pressure, which is 101.3 kilopascal. Only when the pressure that is acting on the surface of the water is 101.3 kilopascal, only then their water will boil at 100 degrees Celsius. But if we change this will also change. Let's say the value of the pressure that is acting on the surface of the water goes up. The boiling point of water will also go up, and the vice versa is also true. If the pressure that is acting on the surface of the water is going down, the boiling point will also go down. So 100 degrees Celsius is not the standard boiling point of water. 500 degrees Celsius can be a boiling point of water if the pressure that is acting on the surface of the water allows it to boil at 500 degrees Celsius. So what I'm trying to say is that whenever we want to find the boiling point of water, we have to consider the pressure that is acting the pressure which the water is subjected to. So we are going to start with steam generation, and we are going to look at steam generation using this graph. Here it's temperature, in degrees Celsius, and here it's enthalpy. It's in joules. And enthalpy is the heat energy of steam or water. It is given by H, represented by H, and the general formula is U plus PV, where this is the specific enthalpy and this is the specific internal energy, this is the specific pressure, and this is the specific volume. So what we are going to do is we want to generate steam, and the way we generate steam is by adding heat energy to water and converting that water to steam. So we are going to start with water at an unknown temperature. Let's say that water is subjected to atmospheric pressure, meaning its boiling point will be 100 degrees Celsius. So we are starting with water. It is in this. The temperature of water, let's say it's 20 degrees Celsius. It's 20 degrees Celsius, and it is here. What happens to the water when we add heat energy? The water will increase in temperature, and as the temperature is increasing, the enthalpy will also increase. Therefore, we are going to have something like this, which is representing that the temperature is increasing and the enthalpy is increasing. Remember, enthalpy is what? It's the heat energy. It's the energy of water. or energy of steam. So it is increasing because we are adding heat energy to the water, and the temperature is also increasing. The temperature will increase up until we get to the saturation temperature, TS. Saturation temperature is the same thing as the boiling point. Here, this will be 100 degrees Celsius in this case, because we are considering the atmospheric pressure. At this point, the water will stop rising in temperature. Why? Because water cannot have a temperature which is higher than its boiling point. Once we add heat energy to water and we get it to its saturation temperature, the temperature stops rising. And then now, the heat energy that is added after the water has reached its saturation temperature is now used to convert the water to steam. And we're going to have something like this, indicating that heat energy is being added. You can see that the heat is increasing, but the temperature is not increasing. Why? Because the heat energy is added, but is not longer used to change the heat, the temperature of the water, but to convert the water from water to steam. Meaning from here to here, we are having water. And then from here to the point, to this point, we will be having water plus steam. Up until all of the water is converted to steam, and we get to this point where we are now having everything inside, maybe the pot that we are using, being steam. There is no longer water. All the water has been converted to steam. From there, now the heat energy that is added to the pots that we are using is no longer used to convert water to steam, because there is no water to convert. Now the temperature is used to raise the temperature. The heat energy is used to raise the temperature of the steam. And that temperature, or this point, we are going to say we are having superheated temperature. This will be the temperature of the superheated steam. So what's happening here is that from this point to this point, we are still having water. The water is raised in temperature up until it gets to its saturation temperature. And then from here, let's say this is A, this is B. And then from B to C, we are now having water being converted to steam. And what we have here, we said, is water plus steam. The name that we use for this kind of steam is called wet steam. The reason why we say it's wet steam is because the steam that we have here still contains water droplets. Therefore, it is wet steam, indicating that there is water and steam inside that mixture. And we're going to have a diagram like this. This is what will give us what we call our dryness factor, or our dryness fraction. What we are saying is that the more heat energy we add from this point, from point B, is the less water we will be having. At this point, since we can see it's 50-50, we will be having 50% of steam and 50% of water, meaning 50% of the water that was in the pot has now been converted to steam, and 50% of the water is yet to be converted to steam. We still have 50% being water and 50% has already been converted to steam. Therefore, we have something we call the dryness factor. The dryness factor or dryness fraction is what we use to indicate how much water is still there and how much of it has now been converted to steam. So if we get a dryness fraction of 0.2, this tells us that only 20% of the water has been converted to steam, meaning 20% of this mixture is steam and 80% of it is what is water. If we are going to have a dryness fraction of 0.5, this is telling us that it's 50-50. 0.8, 80% of it is steam, and 0.9, 90% of it is steam. And then at this point, 100% of it is steam. Therefore, the steam that we get here, we call it dry steam. The steam that we get as C, we call it dry saturated steam. The reason why it is dry saturated, it is because there is no longer water in the steam. It's pure steam, 100% steam. And it is saturated because, yes, it is 100% steam, but it still has the temperature of the saturation temperature, which is 100 degrees Celsius. So now, from here, the heat energy that is added from point C, because there is no longer water to be converted to steam, is now used to raise the temperature of that steam from point C to point D. And from point C to point D, that is where we have what we call superheated steam. Superheated steam. The reason why we call it superheated steam is because it has a temperature that is higher than its saturation temperature. Every steam that has a temperature that is higher than its saturation temperature is called superheated steam. So here we are having water. All of this is water. And then here we are having water plus steam. As the graph is moving in that position, in that direction, it indicates that water, it's being converted to steam. The more we go in that direction, the less water we have and the more steam we have, because the more water is now being converted to steam. And we use the dryness fraction to know how much of the water or how much of it is now steam. The heat energy that we add from A to B, we call it the sensible heat. And the heat energy that we add from B to D, we call it latent heat. The heat energy that we add from C to D, we call it sensible heat again. Sensible heat is associated with temperature change. From A to B, heat was added and the temperature changed. From C to D, heat was added and the temperature changed. Latent heat is associated with phase change. From B to C, heat was added, but temperature didn't change. What was happening? Water was being converted to steam. So we were changing from the phase of liquid to the phase of gas. Latent heat is associated with phase change, and sensible heat is associated with temperature change. Now let's talk about the formulas that we will be using in this section. We said H represent enthalpy, and enthalpy is the heat energy of water. This section, we said only water exists. So the enthalpy of water is represented by HF. F is the suffix that we use to show that we are dealing with water. It means it's the enthalpy of water, or the heat energy of water. It's called the liquid enthalpy. And here, because we have water and gas, or water and steam, the mixture of water and steam, we are going to use HFG, because we know that we have water. Water is represented by F, plus steam. Steam is represented by G. So at point C, we said we are having dry steam. From here to here, that will be the enthalpy of dry steam. The enthalpy of dry steam is represented by G. Therefore, Hg, which is the dry steam, covers the HFG and HF. Therefore, Hg, the formula for Hg is equals to HF plus HFG. And then from C to D, we have, not from C to D, at point D rather, there we are having what? Superheated steam. It's H sup, and H sup covers what? It covers HF and the heat energy that is added from point C to D. So we're going to have a formula that looks like this for H sup plus specific heat capacity of the superheated steam times the change in temperature, which will be T sup minus the saturation temperature. That is the enthalpy at D. And for wet steam, will be having the enthalpy that was added from point A to point B, which is HF, and then depending on how much of that is steam, we will be having the dryness fraction represented by X times HFG. Now this is HFG. If we were to say HF plus HFG, that will give us dry steam. But we include the dryness fraction because we want to know how much of the HFG are we having, depending on the dryness factor, or depending on how much of it is now dry steam. Therefore, the equation will be H wet is equals to HF plus X times HFG. So if we were to be asked for the heat energy that is needed to get the steam from point C to point D, which is the heat energy that is needed, the additional heat energy that is needed to overheat the steam, to take it from dry steam to superheated from point C to point D, that, let's say, is going to be, let's name it HSS. That will be this part. Remember, at C, this is the enthalpy. We added this heat energy to take it from point C to point D. Therefore, we are going to say HSS is the specific heat capacity of superheated steam times T soup minus the saturation temperature. Or we can say H soup minus Hg. It's also the same thing. If we have this information, we can use this, but if we are given H soup plus the enthalpy of the dry steam, we can use this one. Depending on what you have, you can choose which formula you are going to use. So another formula that we will need to know is, if they are asking us that from the wet steam that we have, how much energy will we need to dry the steam, we are going to use this formula that says HFG minus X HFG. And that is everything that we will need to start with the heat, the steam part of heat. And most of these, what we're talking about, might not make sense at this point, but as we continue with the videos and do exercises, we will get to understand how all of this, what we have, is applied, because that is the very important part. You have to know how to apply them. It doesn't help to knowing this from A to B without you knowing how to apply them. So from here, this will be the end of this video. Going on, we will be doing questions, learning how to apply these things, and I will see you on those videos.